Okay, let's dive right into this. Welcome to another explainer, where we are going to unlock the hidden physics that drive every single breeze, storm, and weather pattern on our planet. Today, we are looking at the Earth not just as a rock floating in space, but as a massive, intricate machine, a global wind machine. It is a system perfectly designed to keep us alive, and the mechanics behind how it works are absolutely fascinating.
To really understand this machine, we have to start with the ultimate mystery. Think about it for a second. Why doesn't the Earth's equator just slowly boil away over time? Or on the flip side, why don't the poles just permanently freeze over into solid blocks of ice? The planet has this massive continuous heat imbalance. Today, we're going to solve the mystery of exactly how our atmosphere handles that immense tension. And it all begins with one fundamental spark.
That brings us to Section 1, the spark, or insolation. This incoming solar radiation is the very first push in a giant domino effect that creates literally all of our daily weather.
Now, there is a super common myth out there that how close we are to the sun dictates how hot our weather is, but it's actually not true. During its orbit, the Earth is actually farthest from the sun, about 152 million kilometers away, on July 4th, which is a position we call aphelion. Conversely, it's closest to the sun, or at perihelion, on January 3rd, at roughly 147 million kilometers. You might think this means January should be globally scorching. However, the effect of this distance variation is actually totally masked by the distribution of land and sea and by our atmospheric circulation, so our physical distance from the sun doesn't actually dictate our daily weather changes on the surface at all.
Instead, the real secret is all about the angle. Because the Earth is shaped like a sphere, the sun's rays hit the top of our atmosphere at totally different angles depending on your latitude. At higher latitudes, closer to the poles, the sun's rays come in at a slant. These slant rays have to spread their energy out over a much wider area compared to the direct vertical rays hitting the equator. Plus, those slant rays are forced to pass through a much greater depth of the atmosphere, which means way more of that energy is absorbed, scattered, and diffused before it ever even reaches the ground.
And actually, speaking of scattering, this process gives us one of the absolute coolest phenomena on Earth. As those rays pass through the troposphere, very small suspended particles physically scatter the visible spectrum of light. This is exactly what paints our sky blue during the day, and it's what gives us those brilliant red colors when the sun is rising and setting at a really sharp slant.
To put this energy gap into perspective, just think about the sheer scale of the numbers here. In the tropics, the incoming energy is about 320 watts per square meter. Up at the poles, a measly 70 watts per square meter. That is a staggering difference in energy, and it completely sets the stage for everything our atmosphere has to do next.
All right, moving on to Section 2, the heat transfer, or what we call bottom-up heating. It's a completely counterintuitive reality, but the sun does not directly heat the air. Our atmosphere is literally heated from the ground up.
This bottom-up heating happens through three distinct mechanics. First is conduction, where the air in direct physical contact with the warm land slowly heats up. Next is convection. As that air heats, it rises vertically in currents, carrying warmth up into the troposphere. But the third one, advection, is the horizontal movement of air, and it's highly influential. In middle latitudes, advection drives almost all of our day-to-night weather variations. It is even responsible for the intensely hot local summer winds in northern India that are known as the Lu.
Part 3. Mapping Earth's temperature. To really see the big picture of how this heat moves, meteorologists visualize it using isotherms, which are just lines connecting places that have the exact same temperature. When we draw out those maps, we establish the great tension in our story. Right between 40 degrees north and 40 degrees south latitude, the Earth has a massive net radiation surplus. It takes in way more heat than it loses. Meanwhile, the regions near the poles have a severe net radiation deficit. If nothing intervened to fix this, the tropics would eventually boil and the high latitudes would permanently freeze solid.
But before we look at the planet's grand solution to this, let's take a quick detour into a fascinating local phenomenon called the inversion of temperature. Normally, temperature decreases as you go higher up in the sky, about 6.5 degrees Celsius for every 1,000 meters. But sometimes, especially on long, clear winter nights, the Earth cools off so rapidly that by early morning, the ground is actually cooler than the air above it. This traps a layer of cold air underneath a ceiling of warmer air. This inversion traps dust and smoke, creating those really dense morning fogs. Up in the mountains, cold heavy air will literally flow down slopes like water into the valleys. It's a process called air drainage, and it actually protects mountain plants from frost damage. Pretty cool, right? Okay, back to the big picture. Section 4. The release valves, pressure and wind. How exactly does the planet prevent itself from overheating? It's all through pressure differences that trigger our winds.
The entire globe is wrapped in these invisible pressure belts. You have the equatorial low right at sea level near the equator, subtropical highs at roughly 30 degrees north and south, subpolar lows at 60 degrees, and the polar highs at the very top and bottom of the world. What's absolutely amazing is that these aren't permanent fixtures. They physically oscillate. They shift southwards in the winter and northwards in the summer, perfectly following the apparent movement of the sun.
Just like we use isotherms for temperature, we use isobars to track pressure. These are lines connecting places of equal pressure. Now the key here is the pressure gradient, which is simply the rate of change of pressure over a distance. When you see isobars tightly packed together, the pressure gradient is incredibly strong, and that violently pushes the air, resulting in really high wind velocities.
Which brings us to Section 5, winds and the Coriolis force. If pressure was the only boss in town, winds would just blow in straight lines. But they don't.
As the wind begins to blow due to those pressure differences, the Earth is physically spinning beneath it. This rotation exerts the Coriolis force. So the absolute crucial point here is that this force acts totally perpendicular to the pressure gradient force. It acts as the ultimate steering wheel, constantly pushing the wind off its straight-line path. Because of the geometry of our rotating sphere, this deflection operates uniquely depending on exactly where you are standing. In the northern hemisphere, winds are consistently deflected to their right. In the southern hemisphere, they're deflected to their left. The force is strongest at the poles, but get this, right at the equator, the Coriolis force is exactly 0.
And that 0 value leads to a seriously surprising fact. You will literally never see a tropical cyclone form right at the equator. Why? Because without the Coriolis force to bend the winds and create that massive spinning effect, the winds just blow straight into the low pressure zones. The low pressure simply fills up with air instead of intensifying into a massive spinning storm.
Now, if you travel about 2 to 3 kilometers up into the sky, safely away from the friction of the Earth's surface, something beautiful happens. The pressure gradient, pushing the wind, is perfectly balanced out by the Coriolis force, pushing it sideways. The result is what we call geostrophic wind. This is wind that blows perfectly parallel to straight isobars, trapped in a high-speed balancing act. Back down near the surface, though, we see 2 massive circulation patterns. In a cyclonic circulation, winds converge around a low-pressure area and are physically forced to rise. This rising air is essential for forming the clouds and precipitation you see outside your window right now. In an anticyclonic circulation, it's the opposite. Air over a high-pressure area subsides from above and diverges outwards at the surface, which typically brings clear, sunny skies. And that right there brings us to the grand climax of this entire cause and effect chain. As the source material so beautifully puts it, the wind redistributes the heat and moisture across the planet, thereby maintaining a constant temperature for the planet as a whole. All the pressure belts, the Coriolis deflection, the rising and falling air, they are the Earth's vital distribution network. They take that massive heat surplus from the equator and carry it poleward, quite literally saving the planet from both freezing and boiling.
We are basically living inside a spectacular, self-regulating thermal engine. It is a system of perfect balances and counterweights. So I want to leave you with this one thought to take away from this explainer today. Next time you step outside and feel a sudden breeze on your face, just pause for a second and ask yourself, what distant part of the planet is trying to cool down right now? Thanks so much for exploring this with me. Keep wondering, keep learning, and I'll catch you on the next one.